Welcome! In this session, we'll tackle problem number 86, partition list. This is a linked list problem that challenges us to partition nodes based on a given value while maintaining their relative order. Let's dive in and explore the problem, break it down, and identify the best solution together. In this problem, we are tasked with partitioning a singly linked list based on a given value, x. The goal is to reorganize the list so that all nodes with values less than x appear before those with values greater than or equal to x. Importantly, we must maintain the original relative order of nodes within each partition. The input consists of the head of the linked list, representing its starting point, and the integer x, which acts as the partitioning threshold. The output will be the head of the modified linked list after applying the partitioning logic. Here's an example to understand the concept. Suppose the input linked list is 1-4-3-2-5-2 and the partition value, x, is 3. The output linked list should be rearranged as 1-2-2-4-3-5. The explanation is as follows: nodes with values less than 3 are moved to form the left partition, which includes 1, 2, and 2. Meanwhile, nodes with values greater than or equal to 3 form the right partition, which includes 4, 3, and 5. Notice that within each partition, the relative order of nodes remains unchanged from the input list. Let's look at another example. If the input linked list is 2-1 and x is 2, the output becomes 1-2. In this scenario, nodes with values less than 2 form the left partition, which is just the node 1. The remaining node 2, being greater than or equal to the partition value, forms the right partition. Again, the relative order within each partition is preserved, which is why the output list mirrors the input structure in this case. Now consider a slightly more complex example. For the input linked list 5-8-5-10-2-1 and x equal to 5, the output linked list becomes 2-1-5-8-5-10. Here, the nodes with values less than 5, specifically 2 and 1, move to the left partition. The nodes with values greater than or equal to 5, including 5, 8, 5, and 10, form the right partition. The original relative order within each partition remains intact, ensuring that the output list is a properly partitioned version of the input. There are a few edge cases to consider. First, if the input linked list is empty, the output should also be an empty list. Second, if all nodes in the list have values less than x, the output should remain unchanged, as the entire list already forms the left partition. Similarly, if all nodes have values greater than or equal to x, the list also remains unchanged as it naturally forms the right partition. It's also important to note that the value x does not need to appear in the list for partitioning to occur. Lastly, the algorithm should handle large ranges of values for both the node values and x, including very large positive and negative integers. To start, we considered a brute force approach to solve the problem. The intuition here involves iterating over the linked list multiple times. First, we separate the nodes into two groups, one containing nodes with values less than x and the other containing nodes with values greater than or equal to x. Then, we reconstruct the original list by iterating through these groups and joining them. While this approach seems straightforward, it has several drawbacks. It requires multiple traversals of the list, which reduces efficiency. Additionally, it introduces space overhead since we need temporary storage for the two groups, and this violates the in-place requirement of the problem. Finally, the time complexity can degrade to O, in superscript 2, in the worst case if the list is reconstructed repeatedly. These inefficiencies make this approach problematic for larger inputs. Now, to achieve a more efficient solution, we use the two-pointers approach with a single linear traversal. The key idea is to create two dummy nodes, before and after, which act as placeholders for two separate lists, one for nodes with values less than x, and another for nodes with values greater than or equal to x. These dummy nodes simplify the process of building the partitions. Using two pointers, before_ptr and after_ptr, we dynamically construct the two lists as we traverse the original linked list. For each node, if the value is less than x, it is appended to the before list. Otherwise, it is appended to the after list. Once the traversal is complete, we connect the two lists by linking the before list to the after list. To ensure the final list terminates properly, we set the next pointer of the last node in the after list to none. This approach not only achieves an O(n) time complexity by using a single traversal, but it also operates in place without requiring extra storage for the nodes. Another advantage is that it preserves the relative order of nodes within each partition, which is a key requirement. The two pointers with linear traversal approach was chosen as the final strategy because it is the most efficient and elegant solution. It satisfies all the problem constraints, including preserving the relative order of nodes and operating with O(1) extra space. Compared to the brute force method, it eliminates the inefficiencies of multiple traversals and avoids the complexities associated with reconstructing the list. One of the key insights in this approach is the use of dummy nodes, which simplifies partitioning and eliminates the need for special handling of edge cases, such as empty lists or scenarios where all nodes fall into one partition. This realization was a major aha moment, as it reduced the problem to a straightforward single traversal task. When comparing the brute force and optimized approaches, the differences are clear. The brute force method is inefficient, with O(n) superscript 2 time complexity and additional space requirements, while the two-pointers approach offers O(n) time complexity and in-place construction. Furthermore, this method strikes an excellent balance between simplicity of implementation and optimal performance, making it the clear choice for solving this problem. This problem serves as a great example of how dummy nodes and pointer manipulation can simplify operations on linked lists. The two-pointers approach is not only a textbook solution for partitioning problems, but it also showcases how clarity, efficiency, and adherence to constraints can be achieved simultaneously. By leveraging these techniques, we can handle linked list problems more effectively, making this approach a valuable addition to your problem-solving toolkit. The problem we're solving here is to partition a singly linked list around a given value, x. The goal is to rearrange the nodes so that all nodes with values less than x come before nodes with values greater than or equal to x. It's important to maintain the relative order of nodes within each partition as they appear in the original list. To summarize, the input is a linked list and an integer x, and the output is a reordered linked list that meets these criteria. To solve this, we can use two pointers or dummy nodes to create two separate partitions, one for nodes with values less than x and another for nodes with values greater than or equal to x. As we traverse the input list, we append each node to the appropriate partition. After processing all nodes, we combine these two partitions into a single reordered linked list. To make this process easier, we initialize two dummy nodes, less_head for the less than partition and greater_head for the greater than or equal to partition. We also use two pointers, less and greater, to track the current ends of these partitions. By traversing the list just once, we efficiently append nodes to the correct partition using these pointers. After traversing the entire input list, the next step is to connect the two partitions. We attach the end of the less than partition to the start of the greater than or equal to partition. Additionally, we ensure that the last node in the greater than or equal to partition has its next pointer set to none, which properly terminates the linked list. The final result is returned by pointing to the node that comes after the less_head dummy node. By appending nodes in the order they appear during traversal, the algorithm guarantees that the relative order of nodes within each partition is preserved. The use of dummy nodes simplifies the implementation by eliminating edge cases, such as handling the first node separately. Also, the algorithm processes each node exactly once, ensuring a time complexity of O(n). This approach relies on a few key data structures. Dummy nodes are used to simplify the process of appending nodes to the partitions, as they eliminate the need to check whether a partition is empty before adding a node. The pointers less and greater help track the current ends of the respective partitions, ensuring efficient O(1) insertion. The algorithm also handles various edge cases seamlessly. For example, if the input list is empty, the function simply returns none. If all nodes are either less than x or greater than or equal to x, only one partition will have nodes, but the algorithm still works correctly. Duplicate values are handled properly, with those equal to x being placed in the greater than or equal to partition while maintaining their relative order. Let's analyze the complexity of this algorithm. The time complexity is O(n), where n is the number of nodes in the input list. This is because we traverse the list exactly once, processing each node in constant time. The space complexity is O(1), as the algorithm uses only a constant amount of extra space for the dummy nodes and pointers. Now, let's consider an example to better understand how this works. Suppose the input linked list is 1-4-3-2-5-2, and the partition value x is 3. Here's how the algorithm processes the example step by step. First, we create dummy nodes less_head and greater_head. Then, as we traverse the list, we encounter each node and add it to the appropriate partition. Node 1 is added to the less partition. Node 4 goes to the greater partition, as does node 3. Node 2 is added to the less partition, while node 5 is added to the greater partition. Finally, the last node 2 is added to the less partition. After processing all nodes, we connect the less and greater partitions, resulting in the reordered list 1-2-2-4-3-5. This approach is both efficient and easy to implement, ensuring stable partitioning and optimal performance. Here, we start by defining a list node class, which represents each node in our linked list. The val attribute stores the node's value, and next points to the next node in the list. Next, we define the partition method within a solution class. This function takes two inputs, head, which is the head of the linked list, and x, the partition value. The goal is to rearrange the list so that all nodes with values less than x come before nodes with values greater than or equal to x, while preserving the original relative order of nodes in each group. To achieve this, we create two dummy nodes, less_head and greater_head. These will act as the starting points for two separate lists, one for nodes with values less than x and another for nodes with values greater than or equal to x. We also initialize less and greater pointers to help build these lists. Now, as we traverse the original list using the current pointer, we check each node's value. If the value is less than x, we append the node to the less list and move the less pointer forward. Otherwise, we append the node to the greater list and move the greater pointer forward. The current pointer is then updated to the next node in the list, and this process continues until we've gone through all the nodes. Once the traversal is complete, we need to connect the two partitions. To do this, we set the next pointer of the last node in the less list to point to the start of the greater list. This is done by linking less.next to greater_head.next, effectively merging the two lists. Next, we terminate the greater list by setting greater.next to none. This step is crucial to avoid any potential cycles in the linked list, ensuring a proper termination. Finally, we return the start of the less list by returning less_head.next. This effectively skips the dummy node we initially created and provides the head of our newly partitioned list. With this implementation, the linked list is successfully rearranged according to the problem's requirements while maintaining the relative order of nodes within each partition. Here, we begin our Java implementation by defining the structure of a singly linked list through the listNode class. Each node contains an integer value and a reference to the next node in the list. Moving to the partition method, this function takes in the head of the linked list and an integer x, which serves as the pivot value for partitioning. To facilitate the separation of nodes, we create two dummy nodes, lessHead and greaterHead. These act as starting points for two distinct lists, one for nodes with values less than x and another for nodes with values greater than or equal to x. We also define two pointers, less and greater, initialized to these dummy nodes, which will help us construct the respective lists dynamically. Next, we begin traversing the original linked list using a pointer called current. For each node, we check its value. If the value is less than x, the node is added to the less list by updating the next pointer of the less node, and we move the less pointer forward. If the value of the current node is greater than or equal to x, it is added to the greater list instead. This is done by updating the next pointer of the greater node and advancing the greater pointer. After processing the current node, we move to the next node in the original list using current.next. Once all nodes have been traversed, we connect the less list to the greater list by updating the next pointer of the last node in the less list to point to the start of the greater list, which is accessed through greaterHead.next. To prevent any potential cycles in the list, we ensure that the next pointer of the last node in the greater list is set to null. Finally, we return the merged list starting from lessHead.next, which skips the dummy node and points directly to the first meaningful node in the less list. To begin solving this problem, we first initialize two dummy nodes, less_head and greater_head, both with a value of 0. These will serve as the starting points for two separate linked lists. The less pointer starts at less_head, and the greater pointer starts at greater_head. We also set current to point to the head of the input linked list, which initially points to the node with value 1. Now, as we process the nodes one by one, the first node has a value of 1. Since 1 is less than 3, we append this node to the less list by setting less dot next to current. This moves the less pointer forward to the node with value 1. Then, we move the current pointer to the next node, which has a value of 4. For this node, since 4 is greater than or equal to 3, we append it to the greater list. We do this by setting greater dot next to current, which advances the greater pointer to the node with value 4. Finally, we move current to the next node, which has a value of 3. Next, we process the node with a value of 3. Since 3 is equal to 3, it is appended to the greater list. We set greater dot next to current, which moves the greater pointer to the node with value 3, and then move current to the next node, which has a value of 2. This time, since 2 is less than 3, it is appended to the less list. We set less dot next to current, advancing the less pointer to the node with value 2, and move current to the next node, which has a value of 5. For the node with value 5, since 5 is greater than or equal to 3, it is appended to the greater list. We set greater dot next to current, moving the greater pointer to the node with value 5. Finally, we process the last node, which has a value of 2. Since 2 is less than 3, it is appended to the less list. We set less dot next to current, advancing the less pointer to the node with value 2. At this point, current is moved to none, indicating that we have reached the end of the input list. Now that we have processed all the nodes, the next step is to combine the two lists into the desired output order. To do this, we connect the less list to the greater list by setting less dot next to greater_head dot next, which skips over the dummy greater_head node and directly links to the first node in the greater list. We also terminate the greater list by setting greater dot next to none, ensuring there are no stray connections. Finally, we return less_head dot next as the new head of the modified list, skipping the dummy less_head node. The intermediate lists at this stage look as follows. The less list contains the nodes 1-2-2, and the greater list contains the nodes 4-3-5. When combined, the resulting list is 1-2-2-4-3-5. Now, let's explore two special cases to understand how the solution handles edge scenarios. In the first example, all nodes in the input list have values less than x. For the input 1, 2, 2, with x equals 3, every node satisfies val x. As a result, all nodes are appended to the less list, while the greater list remains empty. The final combined list is simply 1-2-2. In the second example, all nodes in the input list have values greater than or equal to x. For the input 4, 5, 6, with x equals 3, every node satisfies val equals x. All nodes are appended to the greater list, while the less list remains empty. The final combined list remains 4-5-6. These examples demonstrate how the algorithm correctly handles cases where all nodes fall entirely into one of the two partitions. The time complexity of this solution is O(n), where n is the number of nodes in the input linked list. This stems from the fact that we traverse the list just once to partition the nodes. Let's break this down further. First, during the traversal, the while loop processes each node exactly one time. For each node, we perform a constant amount of work, such as checking the node's value, updating pointers, and moving to the next node. These operations collectively contribute to the O(n) cost. After the traversal, we connect the two partitions by updating pointers, such as less.next equals greater_head.next, and terminate the greater partition by setting greater.next equals none. These steps involve only a constant amount of work, or O(1). Since the traversal dominates the runtime, the overall time complexity is O(n). The space complexity of this solution is O(1), meaning the algorithm uses a constant amount of extra space regardless of the size of the input. Let's break this down. First, we create two dummy nodes, less_head and greater_head, to manage the two partitions. These are fixed allocations, so their memory usage is constant, or O(1). Additionally, we use a few pointers less, greater, and current to traverse the list and link the nodes to their respective partitions. These pointers also require constant space. Importantly, the algorithm modifies the input linked list in place without using any additional data structures like arrays or temporary lists. This ensures that the total space complexity remains 1. A brute force or naive approach to solving this problem could involve creating new data structures such as arrays or linked lists to temporarily store nodes that are less than x and nodes that are greater than or equal to x. Afterward, we would reconstruct the final list by combining these temporary lists. While the time complexity of this approach would still be O(n) for traversing the input list and another O(n) for rebuilding the final list, resulting in a total of O(n), the space complexity would be significantly higher. Specifically, we would need O(n) additional space to store the temporary lists during reconstruction. In contrast, the current solution is more optimal in terms of space usage because it avoids creating temporary lists altogether, modifying the input list directly instead. Analyzing the best, average, and worst-case scenarios for this algorithm, we see that the time complexity consistently remains O(n). In the best case, if all the nodes are already in the correct partition order, such as all nodes less than x being at the start and all nodes greater than or equal to x being at the end, the algorithm still traverses the entire list, resulting in O(n) time. In the average case, when nodes are randomly distributed with respect to x, the algorithm processes each node exactly once, maintaining O(n) time complexity. Even in the worst case, where all nodes belong to the same partition, for example, all nodes are less than x or all nodes are greater than or equal to x, the algorithm still performs O(n) work to traverse the list. Mathematically, this is because the algorithm iterates n times through the list, and each iteration involves constant work, giving us O(n) O(1) equals O(n). Meanwhile, the space complexity remains O(1) across all cases, as no additional memory is used proportional to the input size. When tackling the partition list problem, there are several common mistakes to watch out for. First, relying on inefficient brute force solutions such as using nested loops or multiple iterations can lead to time complexities of O(n) squared, or worse. This becomes impractical for large inputs, especially when n exceeds 10 to the power of 5, and can result in failing test cases during interviews or competitive programming. Another frequent issue is overlooking edge cases. For example, forgetting to handle empty arrays, single-element inputs, or specific boundary conditions can lead to unexpected behavior. A typical oversight might be neglecting to check for null or empty inputs in linked list problems. Additionally, some candidates fail to consider space complexity, unnecessarily using auxiliary data structures like hash maps or arrays when an in-place solution is feasible. This adds overhead that could have been avoided. Lastly, errors often arise from assuming properties about the data, such as believing the input is already sorted or mishandling duplicates, which can cause logical flaws in the solution. Another frequent issue to be aware of is off-by-one errors. These are common in scenarios involving indices, where it's easy to accidentally miss the last element or start at the wrong index. Such mistakes can lead to incorrect results or even runtime errors, so it's important to double-check index calculations carefully. Beyond avoiding mistakes, understanding how to excel in interview scenarios is critical. Recognizing common problem-solving patterns, like the sliding window, binary search, dynamic programming, or two-pointer techniques, allows you to quickly identify efficient approaches. Being able to articulate trade-offs between time and space complexity is also essential. For instance, you may prioritize optimizing one over the other depending on the constraints. Don't forget that interviewers value a clear and structured thought process more than just the final answer. Always explain your reasoning, edge case considerations, and algorithm choice. Finally, robust solutions require validation. Be sure to test your approach against edge cases and stress scenarios to confirm its reliability. Understanding related problems can deepen your grasp of the partition list problem and help you recognize patterns. For instance, the two-sum problem, which uses hash maps to achieve O(n) complexity, is an excellent example of optimizing performance with auxiliary data structures. Similarly, the longest substring without repeating characters problem leverages the sliding window technique to efficiently find substrings with unique characters. Merge two sorted lists is another related problem that demonstrates how to efficiently merge linked lists with O(n) time complexity. Finally, the kth largest element in an array problem introduces techniques like using heaps or the quick select algorithm for optimization. Additionally, exploring alternative approaches can expand your problem-solving toolkit. The two-pointer technique is particularly useful for reducing time complexity in problems involving sorted arrays or linked lists, though it often requires pre-processing to sort the data. Hash maps are invaluable for frequency counting or detecting duplicates, but they come with a trade-off of increased space complexity. Divide and conquer strategies, such as those used in merge sort or quick select, break problems into smaller components, but recursive overhead can sometimes outweigh the benefits for simpler problems. Dynamic programming is another powerful technique to consider, especially for problems with overlapping subproblems, such as calculating Fibonacci numbers or solving pathfinding challenges. By storing intermediate results, dynamic programming avoids redundant computations, significantly improving efficiency. However, this approach often requires additional space for memoization or tabulation, which is an important trade-off to keep in mind. Mastering this technique can open up solutions to a wide range of complex problems, making it a valuable addition to your problem-solving repertoire. Great job! Today, we explored the partition list problem and applied an efficient solution. Remember to focus on understanding linked list operations and edge cases. Don't forget to like, share, and subscribe for more problem-solving content. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!